Our objective for this lesson is to write a definite integral that would give us the area of a region between two curves in the xy plane. So how do we do that? Well, what's the problem that we have here? We want to find the area of a region between two curves in the xy plane. So let's take a look at number 3 here. We have the graph of y is equal to negative square root of x plus 7. And then we have the graph of y is equal to the square root of x. So, and then we have x is equal to 0 and x is equal to 9. So if I graph those two equations, I would get two vertical lines. So between these four graphs, 1, 2, 3, and 4, we have this region in the xy plane, and we want to find the area of this region. So how can we do that? That's the question. Now, the problem is this. There is no formula from geometry that would give us the exact area of this region in the xy plane. And the reason for that is because the top and the bottom boundaries of this region are curves and not line segments. If they were line segments, we would have a very simple geometric figure, a trapezoid, and we'd be able to find its exact area very easily by using the formula for the area of a trapezoid. But we have no known formula from geometry to find the area of this region. So the next best thing that we can do is approximate this area. So let's see how that can be accomplished. So one way in which we can approximate the area of the region is to divide the interval from x is equal to 0 to x is equal to 9 into a number of subintervals. So what I've done here is I've divided the interval from 0 to 9 into 9 subintervals of equal widths, the width of each subinterval being 1 unit. And on each subinterval, I have constructed a rectangle, and I can find the area of each rectangle and add the areas of these 9 rectangles and use that sum as an approximation for the area of the region whose exact area I'm looking for. So I want to spend a little bit of time because we want to really develop the definite integral that will give us the exact area of this region. And this development starts with the approximation that I just talked about. And then we consider how we can make that approximation better. And then we take that idea to the extreme by taking the limit of a Riemann sum as the width of the partition, as the norm of the partition approaches 0. And that, by definition, if that limit exists, is a definite integral. So to go through all of those steps smoothly, I want to establish some baseline information. So first of all, we have our interval from x is equal to 0 to x is equal to 9. As you saw earlier, I divided this interval into 9 subintervals of equal widths. When I do that, this is called forming a partition. And these are my partition points. X naught is 0, x sub 1 is 1, x sub 2 is 2, and so on until I get to x sub 9, which is 9. So what is the width of each subinterval? Well, you can just subtract the two x coordinates right minus left. And that's given by delta x sub I, the x coordinate of the right minus the x coordinate of the left. So that's the width of each subinterval. In my case, I have what's called a regular partition because all of my subintervals have equal widths, but you could have a non-regular partition as well. Now, look at how my rectangles were drawn. They were drawn for each subinterval, and for each subinterval, I chose to draw the height of the rectangle so that it was at the right endpoint of each subinterval. But you have some flexibility there. You could have chosen to have drawn it at the left endpoint of each subinterval or even somewhere in between. But The essential thing to understand here is that you divide your interval from 0 to 9 into a number of subintervals, and on each subinterval you construct a rectangle, and you're going to now find the area of each rectangle and add the areas of the 9 rectangles together to get an approximation for the area of the region between the two curves from x is equal to 0 to x is equal to 9. All right, so how do we get this approximation? Well, it's easy enough to just find the area of one rectangle. You would take the height of the rectangle and multiply by the width. But you just have to do that for 9 rectangles and add the 9 areas together. So that's what we're going to do now. Okay, so what is this that we're looking at here? This is called a Riemann sum. It is the sum of products. And each product is going to give us the area of one rectangle. So what we have here is the height of the rectangle multiplied by the width of the rectangle will give us the area of one rectangle, and then we add the areas of 9 rectangles to get an approximation for the area of our region between the two curves. So delta x sub I is the width of each rectangle. And in our case, they're all 1. F of c sub I is going to give us the height of each rectangle. And you have to go back to my previous lesson about finding the length of an arbitrary vertical line segment between two curves to understand that the function that would give us the length or the height of each rectangle is given by f of x is equal to negative 2 times square root of x plus 7. And how do we get that? We just take the y-coordinate of the top endpoint of each vertical line segment and subtract from it the y-coordinate of the bottom endpoint. Top minus bottom will give us the length of a vertical line segment, which in this case is the height of a particular rectangle. So here's the function that we get when we do that. F of x is equal to negative 2 times square root of x plus 7, and that would give us the height of a particular vertical line segment. So that's what we have here. And when we evaluate this function at the proper x values, namely x is equal to 1, 2, 3, 4, 5, 6, 7, 8, all the way to 9, we will get the height of each rectangle in our drawing here. So although you have your choice of drawing the height of the rectangle at any point within each subinterval, I've drawn it so that it's at the right endpoint of each subinterval. So in my case, the sample points at which I'm drawing the heights are equal to whatever I is. So the first sample point is equal to 1. The second sample point is equal to x is equal to 2. The third one is x is equal to 3, and so on. So again, the main thing for you to understand is I have this is called a Riemann sum. And what is this? It is the sum of 9 products, each product giving us the area of one rectangle. So when we find this Riemann sum, we're finding the sum of the areas of the 9 rectangles from my drawing. So now the question is, as we have outlined earlier, how can we get a better approximation? Well, one, it's not a great approximation for us right now because you can see that we're leaving out some area, like above each rectangle and also below each rectangle. The more area we leave out, the less accurate our approximation. So we want our approximation to become more accurate. Well, one way to do that is to go back to your partition, and instead of having a partition that we have now, where we have 9 subintervals of equal widths, I could have 18 subintervals of equal widths. So the width of each subinterval would now be 1/2, and that would be the new height of each rectangle. And I could have not 9, but I could have 18 rectangles. So I'd have more rectangles. I'd have to find the areas of my 18 rectangles and add them together, but it would be a better approximation because I would be leaving less area unaccounted for. Now, we said earlier that we can take this idea to the extreme. What do we mean by that? Well, we can just making our partition have more and more subintervals, and we can have more and more rectangles. So instead of saying 18, we'll just say n rectangles. So now this is called a Riemann sum. It is the sum of n products, each product giving the area of a rectangle, and we have it for n rectangles. And when we take the limit of this Riemann sum, we're going to take this idea to the extreme, and we're going to take the limit of this Riemann sum as the width of the largest subinterval approaches 0. That symbol there, that's called the norm of the partition. It refers to the width of the largest subinterval. When that happens, the number of subintervals will approach infinity, so your approximation will become more and more accurate. And when we take this idea to the extreme, we take the limit of this Riemann sum as the norm of the partition approaches 0, as the number of rectangles approaches infinity. If this limit exists, by definition, it is going to give us a definite integral, and by definition, this is what we would consider the exact area of this region. So we've had a discussion about the theory behind the work that we'll be doing for each problem. And again, to recap, the idea is this. There is no formula in geometry that would give us the exact area of the region that we're interested in. So the best thing that we can do with geometry is to come up with an approximate area for the region, but we can make the approximation better by using more rectangles, and then we can take that idea to the extreme by taking the limit of the Riemann sum that gives us the sum of the areas of the rectangles as the number of rectangles approaches infinity, and that limit, by definition, gives us a definite integral, which will give us the exact area of the region. So that's the theory. So now I want to kind of get us into doing the problems from each assignment mode, okay? So let's say you look at this, and this is the instructions are write a definite integral that will give us the area of the region between the two curves from x is equal to 0 to x is equal to 9. We understand the theory now, but you don't have to go through that thinking process for every single problem. Now that you understand the theory, you can apply it, and you don't have to go through all of the discussion that we've had in your mind, but what you do have to go through is this. I need to write a definite integral that will give me the exact area of this region. How will I do that? How will I do that? So here's how you will do it. You're going to draw a vertical line segment somewhere between the two curves, and then your approximating element is a rectangle, because you're using several rectangles, finding the area of each one and adding them together, right? So basically your definite integral will be like this. You will have a function of x that would give you the height of each rectangle, and then you're going to multiply that by the width of each rectangle, which is found by subtracting the x coordinates of the partition points. That's where the dx comes from. Here it's delta x sub I. That's the width of each rectangle. This is the height of each rectangle. Height times width gives you area of a rectangle, and you're going to do that for a number of rectangles starting at x is equal to 0. So this is called the lower limit of integration, and ending at x is equal to 9. This is called the upper limit of integration. So look at this definite integral. The integrand is a function of x that gives you the height of each rectangle. dx is the width of each rectangle. Height times width is area of each approximating rectangle element. And we're going to start the first rectangle at x is equal to 0 and end with the last rectangle at x is equal to 9. So this definite integral will give us the exact area of the region between these two curves. And for our particular problem, what is the integrand? It is a function of x that would give us the length or the height of each rectangle. And again, how do we get that? We get that by taking the y-coordinate of the point on top and subtracting the y-coordinate of the point on the bottom. And here is what we have. That's our integrand. So in this particular problem, what is our definite integral that will give us the exact area of this region? It is the definite integral of the height function for each rectangle, which is negative 2 times the square root of x plus 7 dx from x is equal to 0 to x is equal to 9. So here is our definite integral that would give us the exact area of the region between these two curves from x is equal to 0 to x is equal to 9.